Hello, everybody. My name is Juan Atalaya. In this opportunity, we'll talk about a correlation metrics tool for error diagnostics and weights in surface codes. During the operation of the distance-wise surface code, we have errors. For example, a phase flip error in this data qubit will flip the measurement outcomes for these two neighboring stabilizers from 1,1 to 0,0. And this flip of the stabilizer readout will be detected as error detection events. In this case, this pair of error detection events happened at the same round, and they defined what we call a space-like pair or edge. Reset and readout errors produce a pair of detection events separated in time by one round and happening at the same stabilizer. These detection events produce a time edge. Errors during the unitary part of the error correction cycle, like CC errors, they can produce two detection events separated in time by one round, and there is also separation in space because these two detection events happen at different major qubits or stabilizers. These edges, we call them ST edges or space-time edges, and they include what is known as hook edges. In addition to these usual error edges, we also find unusual correlations coming from leakage and crosstalk in our experiments. So we have this problem, how to find the error probability Pij for an arbitrary edge between two nodes I and j. And ideally, we would like to find these probabilities from experimental data, and this is our goal. To solve this problem, we assume that the edges are uncorrelated, and then we can describe the statistics of detection events at these two nodes in terms of three effective physical processes. Two of these physical processes affect either node I or j separately, and they are here. We assume that they happen with probabilities Pi and Pj. And the third physical process affects both nodes with a probability Pij. To find this probability Pij, the idea is to express these averages in terms of these three unknown probabilities, and then we end up having a system of a nonlinear system of three equations. And then by solving these system equations analytically, we find the Pij probability, which is given by this expression. What is important here is that the Pij probability is expressed in terms of these experimentally accessible averages. Pij gives the probability of a physical error process involving these nodes I and j, works for repetition in surface code, and can be used for diagnostics and in decoders for the weights. To illustrate the Pij metrics, I consider a 50 rounds distance 25 repetition code experiment. This is the qubit layout for this experiment. The data qubits are indicated by these black dots, and the major qubits by these red dots. The data qubits are joined by this, are along this 1D chain, and then so after running the error correction experiment, we collect the measurement outcomes for the stabilizers or major qubits. From the measurement outcomes, we get detection events, and from the detection events, using the Pij formula I showed before, we get the Pij matrix, which looks like this. The Pij matrix is symmetric, so that's why I'm showing here only half of the Pij matrix. How it looks, the Pij matrix depends on the ordering of the error detection nodes I. Here I'm using the ordering where I collect nodes which belong to the same qubit, and so they define this block, and then this is for the major qubit 1,4, and then I collect the nodes which belong to the next major qubit along the chain, this 2,5, and so on. In each of these blocks, there are many nodes which have different time coordinates, or they are at different rounds. There are many. These are indicated by these minor ticks that you see here, that you better see here. There are many minor ticks because this is for a 50 rounds repetition code experiment. The PAJ probabilities for the time edges can be found near the main diagonal of the PAJ matrix. The main diagonal runs from this corner to this corner. T edges are shifted up from the main diagonal by 1 pixel. S edges and ST edges appear in this qubit block. This block corresponds to detection events happening at these neighboring major qubits 6,3 and 6,1, for example, these two qubits. And the SHs appear along the diagonal of this block, and the STHs are shifted from the space edges just by 1 pixel up. In addition to the PAJ probabilities for these usual edges, we also find other features in the PAJ matrix. For example, these reddish broad features, which indicate the presence of long-time correlations in the detection event data, and this can be attributed to leakage accumulation in the data qubits. Other features are related to crosstalk. For example, this feature indicates that there are some correlation of detection events happening at these major qubits 6,5 and 5,4. They are 5,4 is here, 6,5 is here. So these two major qubits, they are especially closed in space. However, they are far apart along the 1D chain. So these correlations are especially dangerous for error correction because they effectively shortened the code distance. As a second example, here I illustrate the PAJ matrix for a 25 rounds distance 5 surface code experiment. This is the qubit layout. Red dots major qubits, and these black dots are the data qubits. This is how the PAJ matrix looks like. It looks much easier compared to the PAJ matrix for a repetition code, and this is because there are more errors happening in the surface code. The PAJ probabilities for the usual edges can be found, for example, for T edges close to the main diagonal, and for ST and SHs, they can be found along the diagonal of these qubit blocks. We again see these broad reddish features coming from leakage accumulation in the data qubits. PAJ can be used to compare similar quantum error correction experiments. For example, we have done distance 3 surface code experiments in 4 of them in the distance 5 surface code grid. So we have a north distance 3 surface code, south distance 3, east and west. And these are the PAJ matrices for these 4 distance 3 surface codes. So visually, you see that the east, the distance 3, the PAJ matrix looks much cleaner compared to the other ones, especially compared to the north distance 3, where we see that there is a lot of leakage accumulation. And The fact that this east distance 3 looks better can be confirmed when you compute the main error correction metric, which is the logical error probability per round, or also known as logical error rate. For the east distance 3, we find the best logical error rate, or the smallest, 3.2 10 to the minus 2, compared, for example, to the north, which is the worst logical error rate. This PIJ can also be used to benchmark simulations against experiments. Previously, Devere-Caffrey showed how to do comprehensive surface code simulations, which we call Pauli plus because these simulations includes the effects of leakage and crosstalk errors. And what I'm going to tell you now what are the simulation parameters that we use in these Pauli plus simulations. So, for example, for single qubit gates, we independently measure this single qubit gate error average over all single qubit gates, 1.1 10 to the minus 3. Roughly 60% or 2/3 of can be explained in terms of T1, T2 errors, and the rest cannot be explained by our models. So we add in the simulation this amount of depolarizing single qubit errors, just to match what we experimentally observed. No? For CC gates, roughly half can be understood in terms of T1, T2 errors, this incoherent part, plus this contribution coming from crosstalk, and the other half is added in the simulation as the polarizing CC errors. For idle data qubit errors, roughly 80% can be explained in terms of T1, T2 errors, and the rest is added as the polarizing data qubit errors during idle reset time. The reset readout errors are taken from calibration measurements, and here you see the average values over all measured qubits. For leakage, we have two main parameters. This rate is the rate for heating for a process that takes state 1 to state 2. And we have this other parameter, 2 10 to the minus 4, which is the probability to generate leakage at a high frequency qubit of ACC due to qubit defacing. These two numbers are not directly measured, but we take them as reasonable numbers for our experiments. For crosstalk, we have a model which provides crosstalk unitaries, that involve the 4 lowest qubit levels. And here I point out that in our simulation, we use a non-uniform error model, meaning that, for example, for single qubit gates, the different single qubit gates have different error probabilities. These numbers are only the averages over similar components. So after running the Pauli plus simulation, we get a PIJ matrix, and what is shown here is the difference of PIJ for experiment minus Pauli plus. You see that there is presence of long-range correlations from leakage, which are stronger in the experiment or cannot be fully described by the simulation. And after closer inspection, we find that these reddish features comes from leakage accumulation in these two qubits, 2.6 and 2.4. So then this underestimation of leakage in the simulation, especially for these two qubits, 2.6, 2.4, translates into underestimation of the logical error rate by the simulation. This is the experimental number. These logical error rates were obtained using a simple decoder, not the advanced decoders that were used in our main surface code paper. And in the decoding, we use PIJ weights. To improve the agreement between Pauli plus and the experiment from PIJ point of view, we tuned the leakage parameters for these two data qubits by increasing the heating rates. And then we compute this PIJ difference, and we see that now the agreement is much better. There is still some disagreement indicated by these error-diagnostic features. And this indicates that there is still some disagreement between the component error probabilities between experiment and the values assumed in the simulation. For this new Pauli plus simulation with adjusted leakage parameters, we compute the logical error rate again, and now we find that it's closer to the experimental value. So now I will tell you about how to generalize PIJ from H's to clusters of detection events. The idea is similar to the PIJ. For example, let us consider 3 nodes. So besides the single node or 2 node or H processes, now we have a 3-body process which affects the states of these 3 nodes with a probability P1, 2, 3. To describe the detection event statistics of these 3 nodes, we consider 7 independent processes with 7 probabilities, and we find and we express these averages in terms of these 7 unknown probabilities, similar as in the PIJ. And then we have to solve we end up having 7 nonlinear equations with 7 unknowns, which we solve numerically, and then we find the probability for this 3-body cluster, P1, 2, 3. The technique can be generalized to n-body correlations. In that case, we do have 2 to the n-1 equations with 2 to the n-1 unknowns. During the surface code experiment, the data qubits can suffer from Y errors. For example, in this middle data qubit, a Y idle error will produce 4 detection events, this 4-body cluster. And using this generalized PIJ technique, we can find the probability for this 4-body cluster, which in this case is 1.5 10 to the minus 2 for the middle data qubit. And similarly, we can find the probabilities for these Y hyper-H's or clusters. We have used this generalized PIJ up to 4 node correlations in diagnostics and in decoder weights. So in conclusion, the PIJ correlation metrics tool shows the probability of a physical process producing error events at nodes I and J. PIJ can be generalized to analyze arbitrary node correlations from expected errors like Y errors and also unusual errors like leakage and crosstalk. Can be used to find the weights for the decoder, and it's also useful to quantify error probabilities of physical processes. And it is a sensitive diagnostic tool for error correction experiments, which can show, for example, flips of each data or major qubit. Those are the space and time edges, and also diagonal edges from CC errors. The technique can identify purely performing qubits, and it can show evidence of state 2 leakage and crosstalk in the data. Thank you.